All right, it's 10 o'clock on Wednesday, time for another web fireside chat with the experts. And today I have a pleasure to introduce my good friend and our VP of Customer Care, Dave Phillips. And Dave is going to tell us all about how to keep your legacy system alive. It's all yours, Dave.
And good morning to everybody. Thanks for joining us again. Thanks for that nice introduction, Bill. Again, I'm the VP of Customer Care for Creative Electron, and our exciting topic for today is how to make the most of your legacy X-ray system. So the agenda on this will be, we're going to talk about maintenance for your legacy system, training, and then updates. And then we'll have a question and answer session at the end, time permitting. So I hope you enjoy it, and let's get started. So first thing we're taking a look at is a legacy system. So these are some of the legacy systems that we are servicing at Creative Electron, and just kind of giving you a background. If you're in the industry, you may have seen these and been familiar with them. So on the left side, we have the Focalspot Verifier and the Insight series. I came actually from Focalspot. I was the operations manager from 2006 to 2016 when Creative Electron purchased Focalspot. So in this Verifier series, you have probably about 250 of these machines manufactured. So there's quite a bit out there. They're all over the world. You have about 50 of these larger Insight series in all over the world and installed base. And then to the right, we have the NXR 1400, the Nicolet. This used to be called the Kleenex of X-ray. And with these systems, you have the NXR 1400i and the Nicolet 1525. And there's probably about 3,000 of these manufactured. And they started in 1991. And there's still many of them that are still going strong and that we're servicing. So when we talk about these legacy systems, they still have life, and we either continue to repair, do maintenance and training, or we refurbish them and they go back out in the field. Another popular system in the budget realm was the Glenbrook RTX series. There's a wide number of installations of those. And then you come over into the mid to late 90s, you have the CR Technology, CRX 2000, which was a big competitor to Nicolet at the time, and kind of have the same concept with the Faxitron CS100 on the bottom right. This system has a very similar lineage to the Nicolet NXR series, and Dr. Glenn Thomas, that's presented before, has a lot of familiarity with these and the design on that system. So moving on, we were talking about the legacy systems, and the first thing we're going to talk about is maintenance and safety. So what you want to make sure on these systems is you want to make sure they're safe. That is the number one goal when we do service, and make sure they operate correctly. But safety, so what this falls under the radiation safety or the manufacturing of a cabinet radiography system falls under the FDA and CFR 1020.40. And that dictates or gives the requirements for radiation safety, interlocks, and how the system is constructed on that. So the FDA is the umbrella or making sure that all systems in the United States meet these requirements. We want to make sure when we're checking things for radiation safety that all safety interlocks function properly. And the big thing on those interlocks is the one with the load door. So if you're opening up a door, you want to make sure those X-rays turn off immediately on that. And a requirement with interlocks is that that it be dual interlock on a safety door or an access panel that an operator can get to. The other thing is we want to make sure, again, what I was talking about, it's radiation safe. So we use a survey meter, and this one is that survey meter off to the left. and that it meets actual radiation safety with exposure to cabinet or emissions for cabinet radiography. And that happens to be 0.5 MR per hour. And with most of your legacy systems, you'll find, because they are an enclosed lead cabinet with leaded glass, there are really no emissions. It's basically zero. It's ambient radiation on that. It's all enclosed. It's not like going to the dentist where they put a lead skirt over your chest and then x-ray your teeth or do a chest x-ray. Looking back or looking to the right, we have an actual Nicolet system with an NXR 1400 door. And if you take a look on that, you'll see some delamination of that silver area. And then over to more to the right, you'll see some cracks in that door. This obviously is a safety hazard, and we don't want to use this system if it is actually emitting any kind of radiation. Also, you want to check on the systems. Most of them do have a leaded glass. The glass has not been compromised. You can have some scratches, minor scratches, but nothing that goes all the way through, and then making sure that it's not cracked. So once we've made sure the system's safe, we're also doing a preventative maintenance on this system. What we do in the preventative maintenance is we make sure the system is fully operational and it's performing to the original specifications. If it's not performing to the original specifications, we want to make sure it meets the standard of the user so that they can still use the system in a proper way for whatever they're inspecting with their x-rays. And we want to optimize that image train for the resolution, because with x-rays, picture's worth 1,000 words. What we use when we do this preventative maintenance is we use what we call a line pair gauge, and that's that bottom image says line pair resolution gauge. And what this is a line pairs per millimeter. And what that does, as you start at the top and you see these 10 and 20 on the side, as those lines per millimeter converge to the bottom, as you see all those lines go all the way down, and when they stop or when you can't see those lines converge, that's where the resolution stops, where you can see on the image. So we do this each year, annually, when we do a preventative maintenance, sometimes semi-annually, to check the resolution of the system to see if it's degrading or if there's an imaging problem. Could be in the source, could be in a detector, could be in a camera. So the other thing we want to make sure too in that preventative maintenance is the system running smoothly in the X, Y, and Z? Are you able to manipulate those axes and controls? So can you move them smooth? Do the limit switches work? Isn't the system, again, operational? Once we've done the maintenance safety, we can move on to training our operators or an overview. Or excuse me, I skipped one. We can go over to system repair. System repair, when we're doing this maintenance or we're doing the PM or we need a service call, there might be a need to replace the X-ray source. And typically to the right, you'll see 130 kV X-ray source and a 90 kV X-ray source. These are the typical ones used in a legacy system. You also still have some not as typical, the 50, 75, 80 kV X-ray sources. And typically these X-ray sources last 3 to 5 years and approximately 10,000 hours. It just depends on how they're used or abused on that. So they are very robust, but they do wear out. Just think of it as a light bulb with a filament in it, and it burns out at some point. The other thing we can do if we're doing system repair is if we need to replace the image intensifier or the camera. And if you look at that bottom picture, which indicates image intensifier and camera, the cylindrical white part at the top is our image intensifier. The image intensifier takes the X-ray photons and turns them into visible light. It's then collimated in this black area with a collimating lens and a zoom lens, and then a CCD camera on that. So these typically last 10 years. The problem with our image intensifiers is they, the image may have a burn in the image, or the image may degrade. So they may not fail like an X-ray tube, but they do degrade in resolution, and we have a tendency to replace those as the system gets older and older. And the other things that we do in a system repair, if needed be on a service call, we're obviously replacing interlocks for that door to make sure the door shuts off X-rays immediately, and make sure that works correctly for any access points. We also replace control boards. This is usually an analog control board that controls the KV and the MA. You also have wiring harnesses that might be connected to the door opening and closing, that you get motor breaks in the wire, or a harness that goes to a motor. And obviously, as you use electric motors or brushless motors, the motors wear out. So we've repaired our system, we've done our maintenance, and now we want to do operator training, and we want to talk about how to train our operators on our legacy system. So we need an X-ray 101. So the first thing we want to talk to an operator is maybe they've never seen a legacy system, or this is new or refurbished, or you have turnover with your operators. So on this, we first talk about, in the pictorial, we talk about the X-ray tube. So the X-ray tube is at the top. It emits X-ray photons in a cone. We have some sample. This happens to be a circuit board that we're looking at. The X-rays pass through the circuit board. The X-ray photons excite the image intensifier. The image intensifier turns that into visible light. That visible light is seen by our CCD camera and optics, and then piped over to an image processor where we can see it in real time. And what we're looking at when we do X-ray is we're looking at gray levels, and gray levels meaning on a scale from 0 to 255. So perfect black being 0 and pure white being 255. And then we see everything in between on that, on the image. So as we explain to an operator how the X-ray works, I like to use the analogy with a flashlight compared to an X-ray tube. So an X-ray source emits X-ray photons in a cone. A flashlight emits light waves, come out in a cone similarly. If we wanted to project an image of my fingers onto a white wall, the white wall would be the detector, and my sample would be my fingers. If I move my fingers closer to the X-ray source, or the point source, the image on the wall magnifies, and I see a smaller area of my fingertips, but it's magnified and larger. As I move my fingertips farther away, I see a smaller or a larger field of view and less magnification, but more of my fingertips. So this is a good way to explain to an operator that hasn't used X-ray how X-ray theory works. Light waves or X-ray photons, very similar. Continuing on operator training, we want to train our operators for inspection techniques. So we have several inspection techniques that we can talk about, and then we'll go through each one. So top down, 2D imaging, we're looking right down over the top. Oblique viewing, or 2.5D, some people like to call, or compound angle imaging, using magnification, low or high, and then using X-ray penetration, using our kilovolts and our current, or our MA. So top-down imaging. On the pictorial on the left, we have our X-ray source. We have our X-ray photon cone emitting through our circuit board to our detector. And then we have our X-ray image in the middle and an actual picture of the sample that we were taking. So in this top-down view, we can look down. Basically, our top-down view is we're just looking right over the X-ray or the sample, just like if we had a book on a table and we're reading it and we're looking right over on top of the book. So with this top-down view, depending on the magnification, which we'll talk about, or field of view, we can start to see shorts if there's a short on the board, solder balls, things that are not supposed to be there, gross defects. We can see the die attached voiding within these die on that. Basic solder fillet shape, you can see the oval on this, or the ellipse, and the solder fillet shape and size on that. So that's top down. And that's typically where you're just putting the sample, laying it flat, and having the X-rays project to the detector on your sample. Next, we have what everybody likes to call, some people like to call it 3D, but it's oblique or 2.5D imaging. What this does is we have the combination of moving the source, the detector, or the stage. And if you look at the pictorial, in this case, on the left, you can see where we have the ability to tilt our image intensifier, or the detector, which is on the top now, left or right about 45 degrees, and the same with the source. We can also move the source up and down to create magnification, and the detector up and down, but we can also have the ability to rotate that panel or that sample forward and back up to 360 degrees to give a compound angle or an oblique angle. And what that gives us the ability now to do, in this case, is we're looking at a ball grid array or a BGA, is now we can get a pseudo 3D image, and we can visualize the solder fillets, the shape of that solder fillet. You can see some are round, some are cone shaped. We can start to look for opens that mean an open, meaning the space or a gap between the circuit card and the solder spill. We can look for voids, whether the voids are in the base at the circuit board level, the middle, or the top at the component level, and the general shape. So if you take a look on the picture on the right, this is actually the inside view of an inset concept Focalspot system. And the bottom shows the 90 kV X-ray source. And this is tilted approximately 45 degrees. You have a detector on the top, that image intensifier we talked about, the camera, or the collimating lens, the zoom lens, and the camera on top, and we've tilted it. You also have, again, the ability to rotate that board forward and back on that, and that will give you that oblique or 2.5D image on that, and give you much more interpretation or analysis. And again, this is training the operator on this technique. The next, what we talk about is using magnification. So using magnification, low and high, both are good. It just depends on what your inspection techniques and what you're trying to accomplish. So again, if we use that flashlight theory or analogy, the first one, we're doing a high magnification. So we're moving our sample closer to the X-ray source. So we create a larger magnification, but a smaller field of view. And if you take a look at this picture, a high mag picture with a small field of view, you can see, oh yeah, I can see that void on that. And you could probably see that at mid magnification or even low magnification. But then you also see that subtle difference of there's an internal smaller void inside that solder sphere. Also, you can start to see darker and lighter areas within the solder sphere and any anomalies and how the shape is, if there's actually any kind of jagged edges that you might not see if you were doing low magnification or large field of view. Then we go to the bottom where the large field of view is with low magnification. So now we're moving our sample farther away from the X-ray source and closer to the detector so we can see a larger field of view or a larger area of our sample. What this does is gives us the ability to do rapid scanning. Now we can look at the entire component and decide, is there bridging? Are there gross defects? Is there solder balls? Is there a missing solder sphere? Things that we can pick out easily with rapid scanning. And this could be a top-down view, and mostly it is top-down view, but it could be angled depending if you were looking at through holes too. Another technique or training for our operators is using penetration. So using KV and MA. So the KV, what I like to equate our kilovolts is our penetration ability of our X-ray source. So as we talked about when we said that 130 kV or that 90 kV X-ray source, the kilovolts I can equate to an analogy of like a water hose. So you have a water hose and you have water flowing through it. Well, the KV could be what we call the PSI or the pressure, and the MA or the current would be would be the amount of X-ray photons or the volume of water moving through that hose. When you increase KV or MA, you increase the brightness of these X-ray images. So at lower KV, we're looking at, again, what we were talking about, gray levels. So denser objects, when we're not penetrating through as much with that solder, are denser, appear darker on the screen. What we can do with that lower KV is we can look at shapes of the solder spheres, but we can also see those subtle changes maybe in the traces on the circuit board. So how that trace routes to another circuit, or how it routes to another via. Maybe there's a break in that lower KV that you're using. And you can see the shapes, again, better if you're not over penetrating or blooming, what we call. Now, when we go to a higher KV, we're using more penetration of the X-ray photons and usually more current on that. So now we can really visualize these voids inside these solder spheres on that and see the shape. But the other kind of cool thing we can do when we use that higher KV and higher MA is we have the ability to start looking to see, also we have voiding, but we have this inner ring around within the solder sphere. That inner ring is a combination of both the pad at the circuit board interface, the copper pad, and the interface at the component level. So we can see that, and we can see that little feathering or that little outer ring on the other edge, and that tells me the solder sphere or the BGA has collapsed, and also there's large voids on that. So it tells me that I do have reflow. So I have some kind of process going on that. So the circuit card and the component were heated up enough to cause reflow. Now, if that's correct, we're not sure on that. That's a ability depending on the class and what your specifications are. The other thing you can see, and you can see this also on the lower KV image, is that the solder spheres are starting to migrate down towards the trace or the via, and it's stopping at the solder mask. So it tells me these are indicators that we do have reflow and that you train your operator. So again, image interpretation. They've got all these great images, right? They've captured them, but they need to decide what they are. So pretty obvious on the left. Once you explain what voiding is, that outgassing during the reflow process, you can see voids. Now making a determination of what visually, what's passable and what is a failure or what needs to be reworked sometimes can be difficult visually, but at least they have an idea. So you can create a cookbook or a recipe of good images to bad images so that an operator can quickly scan and decide what's okay for visually voiding and what's not okay. And then again, we have our more analysis where we have high magnification of a solder sphere on a BGA. We have that inner ring, which tells me I see the component pad and the combination of component pad and then the circuit card pad. And that voiding tells me I have reflow, and I have that outer perimeter edge, which shows the ball is collapsed. And then again, another upper right, another example of solder spheres and what can be acceptable or not acceptable in a ball grid array, basically doing visual inspection. In the bottom one, we have higher KV and higher MA, but an oblique or 2.5D image where we have the circuit card or the PCB at the bottom, and the component is at the top. And then you have this large void which has migrated or bubbled up to the top of the component level. So now with that 2.5D or that oblique view, you have the ability to see where the voids are in reference into the solder sphere. As opposed when you're looking at these top-down views, you're not able to see where those void locations are. Are they in the middle or are they at the interfaces? Again, image interpretation. So down and dirty, the BGA on the left, for a rapid scan, we can see the whole entire component top-down view. We can see major bridging, some circuit board, on the circuit board, the pads don't have any solder. Some have too much and a lot of bridging. We have solder balls. So we know this for a top-down view and a rapid scan that we could train the operator that this needs to be reworked or scrapped. When you go over to the QFP in the middle, you have an oblique view. You can see a bridge between the two gull wings as annotated by the arrow. But then you go over to the opposite side and you see on the gull wing components that you have a nice solder fillet, both heel and toe. So this is an inspection that you could probably, all of this, you could easily do top down, but it's a nice oblique view that gives you heel and toe and to see how they flowed. Now with the QFN on the right, where the arrows annotate, you're not able to see. You can see the bridging between the two pads as the arrows annotate that. And again, these are all images that can be taken for good to bad, so you can train your operators on how to use the legacy system properly and to interpret your images. Once they've interpreted visually, one more oblique viewing. Again, that 2.5D, we have a good solder spheres on this BGA. They flattened out on the bottom. The ball is collapsed during reflow. We have some voiding, but we have a nice connection. And then we go over to our poor solder joint connection. We start in the corner and it's very round at the bottom. You don't see very much solder, no solder fillet. As you continue on, it gets a little less. And then the one that's annotated suspected open joint is very round and you don't see any solder fillet. So that's basically probably either a gapped or sitting away from the copper pad and not making an electrical connection. So once we've trained our operator to do analysis like this, we have the ability to come over. They've done it visually, but they might go deeper or do more failure analysis or do analysis using an image processor. So our legacy systems have image processors on this, and this is an example of our VIPX image processor. And what we're looking at is a top-down view, and we're looking at a region of interest of a BGA. And obviously this is a big bridge on object 6, and object 6 has passed, has failed. It has a red outline about it because it's failed due to size constrictions or restrictions. If you look at object 16 with a red circle and the red void in the center, this has been set up for criteria. It has failed because of void percentage based on size of the sphere and size of the void. So, and you can do a basic 3D plot of this two-dimensional image. Now we go over to our new TrueView software, which has the ability to do the same type of measurements, but now we have the ability to also come over and do a much more detailed 3D render of that plot and get a much more visually pleasing image. This also has the ability with a newer operating system. So now you've trained your operator. We've talked about maintenance. You've trained your operator to interpret the images and then analyze the images using an image processor tools. Upgrades. So say your system is waxing or waning and not quite up to snuff right now for operation. Well, we have the ability to replace your X-ray source. We can increase the resolution by our X-ray source. Our newer X-ray sources have 5-micron spot size. So the smaller that focal spot size, it increases the resolution. We can increase magnification based on how close it is to the sample. They have much more higher reliability now on this system. And we can also use it as a digital interface with your computer system as opposed to just having analog controls. So it connects through an RS-232 port. And this obviously extends the life of your legacy system as an upgrade. You can also upgrade your detector. With what the big one I talk about is with the Nicolet systems, we can increase our resolution, we can increase our magnification, or if the detector is just at the end of life. What's nice about on the Nicolet systems, by increasing the resolution and magnification, what we can do is the image intensifier in those systems came with a 4-inch input window. Well, the newer detectors have, our image intensifiers have a 4.2-inch input window. So when you switch to 2-inch input window, the field of view is decreased by half, therefore increasing your magnification or doubling your magnification, and then increasing your resolution. This also extends the life of your legacy system. And finally, what we like to do, and we see the most if your system's running properly, is we upgrade the image processor. Typically, these legacy systems that we have out in the field are running Windows XP or Windows 7. So the OS compatibility with your network may not be compatible. And now you can upgrade to a Windows 10. They're plug and play with our legacy systems. It has an RS 170 signal, and it's just converted over, and you can use the new Windows 10 operating system. We have an improved image analysis, like we talked about before, and some different tools, and then you're able to track your time spent on your TPS reports. Finally, is your legacy system up to the task? So, as we talked about, you've done your proper maintenance, you've done your operator training, and your available upgrades. Your system may go on and on and on, right, on that. So, and it's meeting your needs. Like I said, we talked about the Nicolet systems that we have out in the field from 1991. They've done their training, they've done their upgrades, and they've done their maintenance, and they just keep going on and on as a workhorse. If the system's not up to the task and not meeting your expectation or your requirements, you may still have trade-in value where we can talk to you about a new, more advanced X-ray system. And the other thing is, we can talk about those upgrades, or we can also talk about maybe you need a larger board handle, and we can talk about refurbished X-ray systems that we have. I appreciate your time and listening to my presentation and any reference to an office space, if you got that. And if you want to contact me, feel free. My email's there and my phone number, and I look forward to hearing from you. And at this time, I can take questions. And Bill, I guess you'll forward the questions.
Yeah, I have a couple of questions from Danielle. The radiation detector that we use
Yes.
in our PMs, does it have to be calibrated or inspected frequently?
Yes,
Regularly, I should say.
yes, regularly. Yes, it's calibrated. I'm sorry, I didn't mention that, but it's calibrated annually on that, okay, unless there's for something. And so, as I kind of alluded to, our detectors, our PM service is done annually or semi-annually, and that's usually a requirement of all 50 states on that.
And one more question from Danielle. The upgrades that you mentioned, are they only for Creative Electron TrueView products, or do they apply to any brand?
They can apply to any brand on that. So most of what we talked about, those upgrades. So the image processor, as I said at the end, was plug and play. We have ability for all those upgrades for those X-ray sources and detectors on that. And we also have the ability to do, which I didn't mention, but most legacy systems don't use flat panel detectors, which our newer systems do use flat panel detectors. So you do have access to those on that.
Great. I like your message that if you need, if your inspection is fine with the system you have, you're more than happy to keep them alive for as long as you need, right? And then when it comes time to upgrade, we can help you with that as well.
Absolutely, yes. Like I said, there's no, if if it's your Toyota Camry with 300,000 miles and you've done the maintenance and it's working for you, then there's, maybe there's the ability, maybe you do have some new inspection needs, but you continue to keep that system and keep using it, and then upgrade to a new system also. You have them side by side. We have that too. We have a lot of customers where they have both a legacy system and a new system on that. So combinations.
Backup, right? Whenever you have
a backup, or even what if they're just doing some older products, or products that just need to do that, and they don't need that in advanced inspection.
Well, thanks so much for your time, Dave. Awesome presentation. And for those of you listening, if you have any questions, feel free to reach us. Thanks so much, and see you next week. Thank you.
Thanks again thank you.
Great, which one?